Hello everybody, welcome to an introduction to the greedy algorithm. And, well, you might ask, the first thing is, what is a greedy algorithm? Well, it is an algorithm that tries to maximize the solution of a problem. And what are some other techniques that are common with greedy? Well, ad hoc is certainly one of them, and it's not really a topic, but more of a type of problem. And we'll use greedy for ad hoc a lot. What this means is it's just a problem that doesn't really have like a set topic, like graphs or DP or something like that. This is just problem with a random solution. And keep in mind that ad hoc, while it is pretty broad, greedy is also a very broad topic. So it encompasses a wide variety of algorithms. And today we'll be focusing on sort of the easier intro set of them. That doesn't mean they're still hard, because they are, but there are just much harder ones than ones we'll be going over today. So yeah, anyways, ad hoc is just problems with random solutions. And not necessarily random, because you can still spot patterns, but it's just not something that you can directly study for, like a school test. Yeah. Greedy is, again, it is used to optimize a solution. And this can include finding the max, min, and normally when we're trying to find if something is possible or not, we're probably also trying to find the max or min of something. So possible. And that's the main use case of greedy. Greedy pops up on a lot of problems. So it is very wise for you to learn. Anyway, on to the next topic. We'll also be going over some problems on Codeforces, some sample problems on greedy, and we'll be discussing how to implement something like this. And you'll see these two functions in greedy, we will be using this a lot. Use this a lot. Anyway, without further ado, let's get into the problems. Oops. Alright. So, take some time to read the problems now. Alright, so you have enough time to read the problems, then let's get straight to it. So we know that we are given an integer n, and in one move we can do two things. We can divide n by one of its proper divisors, or we can subtract 1 from n. And it turns out we can actually greedily do this. Let's look back here. Let's say, for example, we're given 18. We can greedily do this by dividing 18. Because if it's an even number, we can just divide it by 9, get 2. Use arrow, one arrow represents one operation, and get 1 from that, which represents another operation. And this is true for any even number. This is true for any even number. And this is so powerful. We can also do this with any odd number too. Why? Well, because they tell us in the problem that we can subtract 1 from n. So if we have an odd number, we can make it an even number. So for example, 77, we can make that 76. And then we can divide that by the proper divisor below 76, which will give us 2. And this is the main thing you have to catch. Like, it's like the main observation you have to notice, is that you can make any even number 2 in one operation. And by extension, you can make any even number 1 in 2 operations max. While that's not the same for odd numbers, you can make an odd number, an even number in one operation. So what that ends up saying is that we can make any even number 1 in 2 operations max and any odd number 3 operations max. Now let's look at the edge cases. They tell us that n can be any number from 1 to 10 to the 9th. So it can also be 2, it can be 1, it can be 2, it could be 3. So we need to look at those edge cases to see which ones don't follow this. So let's take n equals 1. That's obviously 0. It's 2, that's 1. It's 3. Well, I can subtract that by 1 2 times. So that's 2 equals 4. Divided by 2 twice, that's 2. It equals 5. Subtract 1, divide by 2 twice. So yeah, everything after this will follow 2 3 2 3. But only these first 3 break the rule. So we need to create special if statements for them. So let's solve the problem now. So they give us a bunch of test cases, so we need to do this. Oops. For an input. Sorry about that. Then we're going to print 0. If n is 2, then we're going to print 1. Print 2. And yeah, that's basically our answer. And we do indeed get that solution. I will move on to the next question now. So that was just, in my opinion, it was a pretty simple example of the greedy algorithm. All right, moving on to the next example now. Give some time to read the problem, and then let's solve it later. All right, so assuming you read the problem now, we know that we have to find the maximum sum of every number in the grid. So what that means is we're probably interested in making all the numbers, as many numbers not negative as possible. And what we're also interested in doing is well, what we can do here is we can choose any 2 adjacent cells and multiply values done by -1. So what that means is that we can make, let me draw a new thing here. We can make 2 negatives a positive, and then we can turn a negative and positive. So if the neg number is here and positive number is here, then we can just solve them. Toss the negative sign to this next number. All right. And that's very powerful because that just basically means that we can play hot potato with the negative sign. And we can, since we can turn 2 negatives into a positive, into 2 positives, that means that if there's an even number of negatives, optimally we're gonna end up with 0 negatives left over, or everything's positive. Alternatively, let's say n is the number of negatives. So if n, then that means that it's all positive. If it's 1, however, or if it's odd, then we have to have 1 negative left over. And what this means is that, and why is this possible? Well, let's look here. So for example, if we have a negative number up here and a negative number down here, and we have positives. Well, we can actually end up playing hot potato with the negative numbers and just passing them on from number to number. So, for example, we can do this in one turn, and then we can do this in the next turn. And we can use any negative number, make them meet up, and then turn them both into positives. Except for one, if there's an odd number. And we can again play hot potato with this negative number. We can make it the minimum value number, like in the grid, in order to reduce its like impact, I guess, on the sum. Because we want to make the sum the maximum. And what that's going to look like is actually going to look something like this. The implementation wise, this is what it's going to look like. And actually, we don't even need to make like a grid and array of arrays for this problem. We can just express this as one big array. And that's due to the fact that it doesn't matter whether it's a grid or it's one long row. Like, we're going to get the same answer from the same numbers, regardless of the grid thing. Because we know we can play hot potato with anything. So let me write that down. Let me write that out here. And what's that give us? N and M, so n lines contain M, which is each. Okay, so we only need M, which is number of lines for chain range. And again, we do this. Or that should just give us our way that we need, and then z equals 0. Unless, yeah, I should make that j. Z equals 0 then. And we're just gonna print out the sum of actually let's just say this. Let's try doing one line actually. Let's do times min. Why do we do this? Well, let's look here. Well, why do we subtract 2 times the minimum? Well, let's look here. So for some random array, like for some random grid, I guess, numbers, I'll just write these things, bar things, as a placeholder for the actual number. So for example, 1 here. When we initially add the sum, here, we're gonna add everything as a positive, even if we want to add it as a negative later. Even if we wanted to add it as a negative later, like in this test case specifically. For example, if we want to, we're gonna add 3 as a positive, but we actually want to add as a negative. So in order to cancel out the positive effect and make it negative, we have to subtract it by itself once so that it's 0, and then by itself a second time so that it becomes negative. So that's basically why. And we should see that we do indeed get these right. Oops. Yeah, why is that happening? All right, let's try this. I'm going to try to be too fancy. Oh yeah, because we only needed to take the first number. solve. It should have actually been something like this. Yeah, we should indeed get the right answer now. Yep, there we go. We do indeed get 2 and 30. That is the solution to this greedy problem, which we used the greedy algorithm for. I might have not mentioned it much because I also focused on solving the actual problem, but it is indeed a greedy problem because we're trying to optimize it. And you kind of have to like learn this after doing a lot of problems. That this just comes by intuition, basically. There's no secret key to learning stuff like this.